And let's get started. So let's just do a quick recap of everything we've been doing in the past week or so. In the past, I think first 2 weeks, we were mainly interested in solving first order differential equations. And really what we were interested in solving were first order scalar differential equations. So anything of the form dx dt is equal to lambda x, where x and lambda were all scalar functions and values. And essentially there were multiple cases that we built up. We started with the homogeneous case. So we started with the homogeneous case. We added some constant input, u, and then we looked at functions u of t. And just to recap these solutions, you might remember now that if we have a homogeneous differential equation, the solution is going to be of the form x of 0 e to the lambda t. We have a constant input. We're able to write the solution as follows. And if we have a functional input, the solution, and this one is like the nasty one where we have this like integral. And here, tau is a dummy variable. All right, so any questions about the scalar process before we start talking about the vector differential equations? All right, if we don't have any specific questions, let's move on to the vector case. And a vector differential equation is essentially one that involves multiple variables. So here we're going to take the derivative of a vector, and that's going to be equal to some matrix A times the same vector. So now we're going to call this a vector X. And again, this is a vector, and the individual entries of these vectors, x1 all the way up to xn, are called the states. So these are called the states. And formally, this is called a state space equation, but we're not going to be talking about state space for a bit. I don't know if this comment was from the earlier discussion, but I shall post a discussion worksheet in the chat anyway.
Sorry, I found it. I just hadn't refreshed the E16B.
Yeah, for sure. No problem. So essentially today, we're going to be looking at vector differential equations where we have the derivative of a vector is equal to a matrix A times the same vector. Any questions about that so far? And I guess the way we're going to do this, it's a bit convoluted, but essentially what we're going to do is we're going to take this vector differential equation and massage it into a scalar differential equation that we already know how to solve. That's just going to be the general idea. So the overall battle plan for today, the way we're going to do this is we're going to take advantage of the eigenvectors and eigenvalues of A. So this matrix A has eigenvectors and eigenvalues, and we're essentially going to learn about something called diagonalization, which is a way to write A as V lambda V inverse, where V is a matrix of eigenvectors, and lambda is a diagonal matrix of eigenvalues. And this diagonal matrix is really going to be the key here. where we're essentially going to define a new variable z in order to set up the differential equation. And if this doesn't make sense right now, let's just take the example, some arbitrary example I'm going to come up with. Let's pick a differential equation like this. And currently, this is a little bit hard to solve because x1's derivative is written in terms of x1 and x2. And x2's derivative is written in terms of x1 and x2 as well. So there isn't a way we can like isolate these variables one by one and like solve for them individually. So what we want to do is we want to somehow set up a vector differential equation of the form dz dt is equal to lambda times z, where lambda is a diagonal matrix. And you might be able to notice here that if your matrix is diagonal, we can break these down into scalar differential equations. Which we already know how to solve from, I guess, over here. So once we solve these will be of the form like k e to the lambda 1t and k e to the lambda 2t. We've solved the differential equation in terms of z, but we want to solve it in terms of x. So if we define a variable z is equal to v inverse x, we can go back by saying x is equal to v times z. So any questions about the big picture plan for today? Okay, moving on. So the way we're going to do this vector differential equation solving is through a technique called diagonalization. And this really is the key to all of this. And essentially, a matrix A is diagonalizable if it has n linearly independent eigenvectors. So just to give an example here, this matrix, like 6, 3, 4, and 5, is diagonalizable since if we were to find the eigenvectors and eigenvalues, these eigenvectors will be linearly independent. So since all of the eigenvectors are linearly independent, you can claim that it's diagonalizable. It's just a definition. And perhaps another example we can give, let's say we had the matrix 2, 1, 0, and 2. This is not diagonalizable. And if you were to actually find the eigenvectors and eigenvalues, you would see that lambda is 2, and we only have one eigenvector, which is in the span of 1, 0. So essentially the eigenspace is one-dimensional. So because we don't have...
Be square?
Sorry?
Does A need to be square?
Yeah, A needs to be square. Okay. So whenever we talk about diagonalizability, we're always assuming A is square. And I think the key here, though, that I want to emphasize here is that we don't have two linearly independent eigenvectors. We only have one. And this is why this matrix is not diagonalizable. And more importantly, the fact we want to use for today is this fact that A can be written as V lambda V inverse, where again, V is this matrix of eigenvectors. And we're going to show how to do this in question 1 of the discussion worksheet today. And as a quick warning, I know these are very, very common mistakes that students make on exams, that essentially not every matrix is diagonalizable. I just gave you one example right here. And there is no relationship between diagonalizability and invertibility. In other words, if a matrix is invertible, you can't say anything about its diagonalizability. And similarly, if a matrix is non-invertible, you can't say anything about its like diagonalizability. So
if we like want to show that a matrix is diagonalizable, do you just find the eigenvectors and show that the eigenspace is the same dimension, has the same dimensions as the thing?
Yeah, exactly. So I think I'll add a note. To show a matrix is diagonalizable, we can show A has n linearly independent eigenvectors. So as we said, if we find n linearly independent eigenvectors of A, the matrix is diagonalizable.
Is n the dimension of A?
Yeah, n is a dimension of A. All right, any other questions for today about diagonalization? It's quite unfortunate that 16A no longer teaches this. I know Math 54 still does, but anyway, moving on, if you don't have any questions. We're going to take a look at discussion 3B, question number 1. And here, question number 1 is going to assume that this matrix A has n linearly independent eigenvectors. And I'm just going to call these eigenpairs. And I don't think eigenpairs is like official terminology, but essentially what I mean is like you have this pair of like lambda 1 and v1 and this pair of lambda n and vn. And the goal of part A is to show that A times V, in other words, the matrix A times the matrix V, where V is a matrix of eigenvectors, is equal to V times the diagonal matrix. And what was I going to say? I think that was about it. To do this, this is a really important matrix trick that I think y'all should know. I think this trick has single-handedly like saved me multiple times in like classes like E127 even. So what this is saying is if you have a matrix A times a vector X, A times X is also going to be a vector. But more importantly, this vector AX can be written as a linear combination of the entries of the vector X. So you can write it as a linear combination of the columns of A, where xi's are the scalars. So this is a really important fact to know about matrix multiplication. And if you aren't quite sure like why this is, I think I would recommend to prove this, to like write out the individual entries like A11, so and so forth. Like, I guess this would be A, yeah. And you can like essentially show that the properties of matrix multiplication like hold if you like multiply this by like x1 to xn. Anyway, with all this in mind, let's actually take a look at the discussion worksheet. And I've just copied over the trick I wanted to talk about over here. So essentially how to do this, let's take a look at A times V. This is going to be equal to A times, I'm just going to rewrite V in terms of its columns. And from the properties of matrix multiplication, if you multiply a matrix A by like its individual columns, you can like distribute it. So you can write this matrix product as AV1 all the way up to AVN. And from here, since we know that VI is an eigenvector of A, you can simplify AV1 as lambda V1 all the way up to lambda N Vn. So this is because of the eigenvector property. So this is what AV is equal to. AV is equal to a matrix with columns lambda 1 V1 all the way up to lambda N Vn. Now let's take a look at V times lambda. And this is going to be equal to, again, let's try writing out the columns of V times a matrix lambda, which is this diagonal matrix with zeros in the gaps. So to do this, let's take a look at V times lambda 1, where this is going to be the first column of lambda. In other words, let's take a look at V times lambda 1, 0, all the way down. And this is going to be where our trick comes in. So maybe my matrix is a little too big. Notice how if we were to write matrix A times X as the following over here, where AX is a linear combination of the columns, we can do the exact same here, where we have a matrix V times lambda. We can write it as a linear combination of these V vectors. So this is going to be equal to lambda 1 V1 plus 0 times V2 all the way to 0 times Vn. And we can just like generalize this to say that like, actually, yeah, so this, since all these weights here are 0, this would just mean that like, this is equal to lambda 1 V1. And we can generalize this to say V times lambda I, where again, this is the ith column of this diagonal matrix, is equal to lambda I, where this is a scalar, or the eigenvalue, times Vi. So if we were to just take a look at everything, this just tells us that V times lambda is in fact equal to lambda 1 V1 all the way up to lambda N Vn, which is exactly equal to what AV was. So we can conclude that AV is equal to V lambda. All right. Now I tried to be as thorough as I can explaining every single step I was doing, but does anyone have any questions about the entire process that we've done so far to show that AV is equal to V lambda? Okay, if we don't have any questions, let's move on to the next part, which says use the fact in part A. So we already know that AV is equal to V lambda, and use this to show that A is equal to V lambda V inverse. And really, all we need to do here is take an inverse, but how do we know V is invertible? So V is invertible since A has n linearly independent eigenvectors. And V is square. So because the matrix is square and has n linearly independent eigenvectors, it has to be invertible. In which case, we can just take AV equals V lambda and right multiply by V inverse. And then we would just get V times V inverse, which is just the identity.
Sorry, Tejan. So why does, because A has n linearly independent eigenvectors, does that also mean it has n distinct eigenvalues? Is that what that means?
Yeah. Or it doesn't, no, actually, yeah. So this is a really great point that I forgot to mention in this discussion. So just because a matrix A has n linearly independent eigenvectors, it doesn't mean it has distinct eigenvalues. So this is a note. A is diagonalizable. In other words, A has linearly independent eigenvectors. Does not imply A has distinct eigenvalues. And if you're unsure why, let's just take A equal to this matrix, for example, where it's 2 times the identity. Then lambda is equal to 2, but we also have eigenvectors.
1, 0, 0, 1.
Yeah, exactly. And I know it, for those who've taken 16A, like in the recent iterations, they've kind of told you to assume if a matrix has distinct eigenvalues, it has n linearly independent eigenvectors. But the converse, having n linearly independent eigenvectors doesn't necessarily imply distinct eigenvalues, and this is the case here.
Okay, then I'm a bit confused about how you made the jump from A having linearly independent eigenvectors to V being invertible.
Yeah, so remember that V is a matrix of eigenvectors.
Oh, that's right. I thought it was the matrix of the eigenvalues. That's why
Yeah.
I was thinking the wrong one. Okay, thanks.
Yeah, no problem. So because V is the matrix of eigenvectors, and all those are linear independent by construction, really, because we assumed A has n linearly independent eigenvectors, this matrix has to be invertible. And this really is the key to writing out A equals V lambda V inverse and solving our vector differential equations. All right, so let's move on to the second question, and I guess what we really came here for today, which is to solve this system of differential equations now. And again, if you don't remember what I guess this was in my other slide, overall plan for today was, we wanted to I guess first write out dx dt is equal to ax. And then to solve this equation, we want to find the eigenvectors and eigenvalues of A. So we're going to do this in our discussion problem. We're going to define a new variable, z equals v inverse x. And now hopefully the V matrix makes a little more sense. This is a matrix of the eigenvectors of A. And then from here, we're going to create a diagonal system where our differential equation is easy to solve over here. And then we're going to convert our solution back into x because we've solved it in terms of z, but we want it in terms of x. So that's the overall plan for today. So I guess how we're going to walk through this together. I'm going to talk about parts A and B, and then and parts A and B are just going to be the setup, find the eigenvectors and eigenvalues. And then I'm going to throw everyone into breakout rooms. We're going to do And in breakout rooms, you're going to talk about how to solve part C, where part C is setting up this diagonal equation and solving the differential equation. So once you figure out how to do that, I think we'll basically be done. Okay, so part A asks us to write out the system of differential equations and the initial conditions in matrix vector form. And this really is just fitting our problem into our form over here. So currently, we know that the derivative of x1 and x2 as a vector is equal to some matrix times x1 and x2. And to get this matrix, we just have to look at these individual equations here. And this should be like similar to what you've seen in like 16a and Math 54, where if you have a system of equations, we can just put that into a matrix. So this is going to be our A, and this is going to be our vector x. And then these variables are going to be the states. And lastly, we want to find the initial conditions. So if our state is a vector x, the initial condition perhaps is x of 0 is just going to be equal to x1 of 0 and x2 of 0. And we're given in this problem that the initial conditions are 3 and 3. So these will be our initial conditions. Okay, any questions about this part? Just the overall setup of dx dt is equal to ax with the initial condition. Okay, if we don't have any questions, the next step in solving is to just find the eigenvalues and eigenvectors of this matrix A. And let's just copy this over. I'm not going to spend too much time on actually solving the eigenvectors and eigenvalues, since this should be familiar or review from 16a or 54, hopefully. But remember that the overall procedure is to just look at the determinant of a minus lambda I, set that equal to 0, and in this case, I'm just going to skip all the math and tell you that this determinant is equal to lambda squared plus 7 lambda plus 10. And if we're to solve this, this tells us that lambda is equal to -2 and -5. And then we want to find the eigenspaces or the eigenvectors. And to find the eigenvectors, we just look at the null space of A, I guess, minus -2i. And in this case, if we just look at A plus 2i, that's going to be like -2, 1, 2, -1. So our first eigenvector is going to be alpha times 1 and 2. And alpha here is just a scalar. So essentially what I'm saying here is any scalar multiple of the vector 1, 2 is an eigenvector. And we can do the same thing for the other eigenvector to say that, hold on a sec, this doesn't look right. Actually, 2. If we add 5, that's a 1. If we add 3, yeah, that's 2. All right, yeah, looks good. This means our second eigenvector, so solving for the null space of A plus 5i, is going to be some constant beta times 1 and -1. In other words, our second eigenvector is going to be in the span of 1 minus 1. And actually, I just noticed I did this in the opposite order, so this is quite important to mention that I'm going to stay consistent with what the solutions are doing because essentially, if you were to do this in the other order, and other order, what I really mean here is just call, which vector I call v1 and which vector I call v2. The results of your diagonalization are going to go in the other order. So whenever you write your V matrix as V1 all the way up to like Vn, make sure the ordering of V1 to Vn matches the ordering of your eigenvalues, lambda 1 to lambda n. So this is really important to remember. If you had swapped the orders of lambda 1 and lambda 2, you would swap the order of the columns as well. So any questions about how to find eigenvalues and eigenvectors and just diagonalization, the ordering of the vectors as a whole? Okay, if we don't have any questions, I think I'll briefly also say that in this case, our V matrix is going to be 1 and minus 1 and 1 and 2. And then our lambda matrix is going to be minus 5, 0, 0, and minus 2. And the next step, as we've been kind of alluding to a lot in, I guess, this discussion, is to define a new variable, z is equal to v inverse x. And we want to use the results of diagonalization to rewrite this differential equation. So we're going to start with dx dt is equal to ax. Define z is equal to v inverse x, and use a is equal to v lambda v inverse to get some goal, and the goal is that dz dt, or I guess d dt of z, doesn't really matter, is equal to lambda times z. So we want to take this, I guess, vector differential equation and convert it into a vector differential equation where our matrix A is a diagonal matrix lambda. And then we need to solve the differential equation in terms of zi, and that you should know how to do from all the scalar examples we've done in the past. So
Is the reason we do the diagonal is just so it's easy to solve? So we just have like one.
Exactly, yeah. That's the whole point we did this.
Okay. So you could, in theory, like just solve it from what you have now. It would just be pretty difficult without doing the diagonalization part.
Without doing the diagonalization, like, we don't really have a methodology to solve this at the moment, right? Like,
yeah.
Because like your states are coupled together. That's like the big issue. So diagonalizing lets us uncouple these one by one. So let's split up everyone into breakout rooms. And in your breakout rooms, I'm going to want you to start here with dx dt equals ax, solve the differential equation, or sorry, rewrite it as a differential equation, dz dt equals lambda z, and then solve it in the easy case. And if you have any questions before joining the breakout rooms, feel free to ask now.
I have a question. For 2b, is that say -51 and -21?
All right, while we wait for everyone else to join the call or rejoin, were people able to solve the differential equations?
So is this question asking how we can get from the start to get to the goal?
Yeah,
Okay, so I thought you would start with saying the z equals v inverse x and take the derivative of both sides.
saying z is equal to z inverse x.
Z equals to v inverse x, and then if you take the derivative of both sides, you have
Yeah,
d dt z equals v inverse d dt x.
yeah,
And then you can substitute that with ax, and then substitute in a, and then the v inverse and v should cancel out.
yeah. That's a great way to do it. I think it's the exact opposite way of how I do it, but this is definitely a valid way to do it as well. So I think everyone is here, so let's go over this together. I think the way I did it was to plug in a into the differential equation. So I plug in v lambda v inverse. And then we can realize that v inverse x is equal to z. And if we left multiply by v inverse, then we get lambda times v inverse x. And this might be a subtle fact that I think some people in the earlier discussion asked about, where if you have a matrix times a derivative, this is the same thing as the derivative of the matrix times the vector. And this is because the derivative is linear, meaning if you take a matrix times the derivative of a vector, like in other words, you have a linear combination of derivatives. And a linear combination of derivatives is the same thing as a derivative of the linear combinations. If you're unsure why that is, just take some time to think about it. But in other words, we can say this is equal to lambda v inverse x, and by substituting in z, we can see that dz dt is equal to lambda z. And again, you could have done this the complete opposite way by starting here, plugging in, I guess, for z as v inverse x and going backwards as well. Either way is fine. Okay, any questions about this part? Anyone want to ask anything in the chat as well? Okay, so moving on.
Do we find the initial conditions in that problem?
Yeah, I think I'll just start it in part D though, because we really are going to use them in part D, right? So the initial conditions, you might wonder how we find these. And we can find these by taking V inverse times the initial conditions in X. So this is going to be V inverse, which I'm just going to write out here to save some time. We took V equal to, actually just copy these over. One, one, negative one, and two. Its inverse is going to be of the form, let's see, 2/3, 1/3, negative 1/3, and 1/3. And then x of 0, if we remember from the beginning, was 3 and 3. So we can just plug that in. And if you do the matrix multiplications, you can show that the initial condition is 1 and 2 in Z. And someone in the breakout rooms asked a really great question. Why do we need the initial conditions for Z? Well, if we take a look at our differential equation right now,
Jason, I think you might have flipped your V which the order of the vectors. So now they don't align with the.
Did I flip the order here?
Maybe not. Maybe I.
I know I flipped them at the last second, so like here to match the solutions. So yeah. Anyway, if we were to look at the individual differential equations here, notice these are scalar equations, but to solve these, you would need the initial conditions in terms of z. And remember the solution is like e to the lambda t. So it's going to be e to the negative 5t and e to the negative 2t. And then we can just plug in our initial conditions here to get z1 is equal to e to the minus 5t, and z2 is equal to 2e to the minus 2t. So this is our solution in terms of z. So any questions about this? We took everything we knew about scalar equations and just solved them as we normally would. And really the last step is to just convert your solutions back into x. So let's perhaps copy this over. So our original differential equation is of the form dx dt is equal to ax. But we want to solve, and we have a solution for z, but we want to solve it for x. So since z was equal to v inverse x, this tells us that x is equal to v times z. And since v was equal to this matrix over here, all it remains to do is just plug the matrix in and multiply everything out. So x is going to be v times z, which is equal to the following. And if you do the matrix multiplications, you're going to get something like e to the minus 5t plus 2e to the minus 2t, and then negative e to the minus 5t plus 4e to the minus 2t. Let's just make sure that matches our solution. Looks like it does. So yeah. Do we have any questions about the overall process? I know this might be an extremely convoluted way to solve vector differential equations. I certainly think it is, where we take a matrix A, find its eigenvalues and eigenvectors, then rewrite it in terms of its, like, I guess, rewrite it as a diagonal matrix equation using the eigenvectors and eigenvalues, solve for those diagonal equations using everything we know about scalar differential equations, since the diagonal matrix lets us turn it into scalar differential equations. And then lastly, we convert our solution back since we solved our solution in terms of z and not x. And last thing I want to say about part F.
Real quick, Tejan.
Yeah.
I noticed that your z is, so it would be a product of a diagonal matrix and a bunch of scalars, right? So why does that result in a column vector and not a diagonal vector? Can you just ignore the zeros?
Are you asking it? Wait, so z here is a vector. And
So
I know,
yeah, so like on the right hand side there, it's a diagonal matrix. So like the diagonal plus a bunch of zeros padded in, and the scalar. Can you just ignore? Oh, never mind. I'm so sorry.
yeah, no worries. I know some people asked in the earlier discussion as well whether z was a matrix or a vector, and
Okay.
z is a vector. And I guess the last comment I wanted to make for part F, which I encourage to do on your own, is we're going to essentially solve the exact same problem, except with guess and check. So this is going to tie everything we did in guess and check in the earlier discussions to how we can use guess and check for vector differential equations. And the main idea I want to talk about is this idea that, remember how we had this diagonal matrix equation. And how the diagonal solution, z, is really equal to k1 e to the lambda 1t all the way down to kn e to the lambda nt, where these k's are scalars. And what this essentially tells us is that if we convert back to x, like x1 and really all the x's, all the states are going to be linear combinations of these functions e to the lambda t. So really, another way to solve these vector differential equations is to, for the 2x2 case, guess x is equal to alpha 1 e to the lambda 1t plus alpha 2 e to the lambda 2t, and so on and so forth. Where all of these values here are scalars that you want to solve for. And you're essentially going to get a system of equations with 4 equations and 4 unknowns, and you should be able to solve for that on your own using the guess and check method. So it's just another way to solve these differential equations much quicker with guess and check instead of doing the whole eigenvector, eigenvalue diagonalization process. I think really what we did here was we showed that the solutions will all be linear combinations of these e to the lambdas. So from here onward, we can always just use guess and check to solve our equations much easier. Okay, that is all I wanted to say for today. It is 12:02, so